Okay, off we go. So last time, let's see here. I got to check it's recording. Okay, so last time. Okay, we're getting started. Thank you. So last time we left off just before section 1.2. I did very little about section 1.1, of course, right? A lot of review and easy stuff in there. So we are going to talk now about something called a parameterization. So it's a different way than you might be familiar with. Different way of representing a curve with algebra. Now, y'all have seen some ways to represent curves with algebra. You've seen, a curve could be written as the graph of a function, or it could be the solution to an equation, something like that. Right? So parameterization is a different way to do this. It is a function where position is a function of what I'm going to call time. Just because it rolls off the tongue a little bit more nicely, it's physically more relatable if you think of it this way. Position is a function of time. Now, to be fair, it could be any single parameter. You can visualize this parameter any way you like. I think it's very convenient to think of it as being time. Okay. All right. So if you think about what this means, then, how would I represent position as a function of time? Well, what's the tip of my finger as I do this motion here, right? At any given moment in time, my finger has a position, right? So a function that gives position as a function of time is literally just kind of tracing out a curve. And I think this is a really nice way to think of a parameterization. A parameterization draws the curve, and when the curve is drawn by a parameterization, we call it a parametric curve. Okay, so position is a function of time. That's all it is. So easy example to get started. Let's look at this one right here. And notice first off the bat, as promised, we have position, x and y. Position in the plane. And both of those coordinates, and therefore the position, are functions of time. And they are functions of time as given by these two formulas. X is given by that formula, function of time. Y by that formula, function of time. So this is what we call a parameterization, and it traces out a parametric curve. Now, next natural question. When you have a parameterization, okay, what curve is it that it traces out? I wish there were a single algorithmic way of figuring that out. I'm sorry to say there is not. There are different points of view that are different, that are useful in different circumstances. So here's one. I mean, you can just kind of notice that, keep in mind, this is what x is, right? Cosine t is representing x, and now, I wanted to switch the color here. Y is, of course, this thing, and that x and that y have a known pre-existing relationship, right? We have this Pythagorean identity on cosine and sine. Cosine squared plus sine squared is 1. So therefore, for this parametric curve, we know this equation is always satisfied. And I just noticed that, right? I didn't derive that. I didn't earn it in some sense, right? It's just, oh, hey, check it out, right? Sometimes that's how progress is made in some cases. So now we know that this is a circle. Be more precise, this is the equation of a circle. So what we have here then is that every point on this parametric curve satisfies this equation of a circle. And now let me say that a little bit differently. Every point on this parametric curve is on the unit circle. So this traces out the unit circle. So the parametric curve here is the unit circle. How are we doing? Are we buying it? Here's another example. Again, notice position is a function of time. Now, oh my gosh, excuse me, I wrote this in a slightly different way here. You'll notice I didn't specifically write x equals, but this is the first coordinate And typically the first coordinate of position is what we call x, not that you have to, but typically, and that's what we're going to do here. And likewise, the second coordinate is y. So don't lose track. It's easy to lose track, but what this is really saying right here is that x equals t minus 1. That is the first coordinate position. So how are we going to figure out what this parameterization traces out? What is the corresponding parametric curve? And there's a different trick for this. There's actually two different tricks I'm going to show you for this. So the first one I'm going to show you is that sometimes, this being a nice example, sometimes you can solve for t in the first equation. You then plug that in for t in the second equation, and then your equation for y becomes a relationship between x and y. And that's just kind of plug it in. Right? You, again, solve for t in the first, plug it into the second. Out pops familiar algebra. Right? This is an equation for whatever our curve is. And then, again, the Algebra 1 memories from high school kick in, and we're like, oh, yeah, that's the equation of a line. Is that cool? All right, now here's a different way to do it for this particular example. Keeping in mind that this is x, and so that what that really says is x equals t minus 1. And you look at the formula we have there for x, you look at the formula we have there for y, both as functions of t, and now I'm going to ask, do you notice any kind of structural relationship between these two functions of t? And yeah, I notice a bunch of relationships. None of them have any trig in them. None of them have any logs. None of them have any higher order terms, right? They're both kind of what you might call first order polynomials of t. And when you notice a relationship like that, they structurally look kind of alike, what that means is you can manipulate the one and turn it into the other. And that's literally what I'm going to do here. I'm going to take this expression that gives the function for x, and I'm just going to fiddle with it. Right? In fact, let me get my screen bigger. There we go. So we fiddle around with this equation. If I take t minus 1, if I multiply by 3, I get this. If I add 7, I get that. Now, of course, you got to be legal. You got to do the same things on the other side. Okay? But the result is exactly the expression for y. And so having kept track of what we were doing on the other side, the nice punchline is we again get a relationship between x and y. And you'll notice, as it should be, we got the same relationship that we did using the other method. So another nice little trick. It's useful on some occasions, not always. None of these methods are useful always, right? That's why I say there is no single method that works. This is I guess I'll introduce y'all to one of my metaphors that I use a lot. I like to talk about everybody collects, knowledge, familiarity with and knowledge of how to use various different tools. And to me, the natural metaphor there is if you're collecting tools, then you're intellectually you're filling up your toolbox. Right? So these are two, I guess we can say three. We have three different tools for your toolbox here, right? And which tool do you use in which circumstance? I don't know. Let the circumstance be your guide, right? If you need to get a screw into a piece of wood, don't use a hammer, right? You got to look at the circumstance and think about, okay, how is this situation tailored for which of the various tools I have? So I will point out, for example, we just happened to get lucky. Happened to get lucky on this one, and I happen to know pre-existing relationships between those formulas. That's what makes that useful. No such luck here. Right? This second method requires that I can actually solve for t. I did here the first equation, could be either, but you do have to actually be able to solve for t, and sometimes you can't do that, right? If you can't solve for t, this is not a good method. Right? And then likewise here, do we see a relationship? Sometimes the answer is no. Sometimes there is no obvious, apparent the formulas just don't look in obvious way just like each other, in which case that wouldn't be a good method. So pick the right tool for the right job, and context is your guide, and there is no algorithmic process for deciding. You just have to think strategically. You don't buy that? Everybody happy? Okay, let's do a three-dimensional one. Here we have a parameterization, I'm going to say in space, because position, you'll notice, has 3 coordinates now. And when position has 3 coordinates, that means that you are in R3. This is tracing out a curve, because of course it is, because that's what parametric curves do, right? They're one input variable, one notion of time. I trace out with my finger a curve. And equations, certainly a single equation, is not set up for defining a curve in space. We're going to see more examples of this as we go on, but an equation in space produces typically a surface. So what are we going to do about this? Different tool for your toolbox. Let's think about what happens if I project down into the XY plane. Now, geometrically, the idea of a projection into the XY plane is that you just kind of smush everything down like this. Just, straight down or straight up if you're below. Just kind of smush everything down into just the XY plane. And algebraically, that means we're going to look just at the X and Y coordinates. Oh my God, I totally recognize that. Right? We saw that. That was our first example. And by the way, this is life is good sometimes. This happens a lot in math. That you just kind of notice, oh yeah, I've already done that one before, right? So we already know that that's tracing out a circle. So we know then that the projection, whatever this curve is, we know that its shadow, if you will, down in the XY plane is a circle. And then likewise, we can talk about the projection to the z-axis. Now, projection to the z-axis means we're going to kind of take all of space and kind of squeeze it in to the z-axis. Said differently, we're going to throw away x and y and look only at z. And that's a pretty easy thing to understand. The z-coordinate is just t. All right, so as time passes, t gets bigger, which means z gets bigger. So so now I have kind of 2 little bits of geometric information about this curve. I still don't know what the curve is, right? But what I do know is that this curve, the altitude rises at a constant rate, and the shadow is doing this move right here. And if you think about it, right, what is it that does that? Well, it's this picture right here, what we call a helix. That is the only curve that has that shadow and that sort of altitude. So this is a by hook or by crook kind of situation. We have now concluded that is a parameterization of this helix. And again, this is a tool for your toolbox. Sometimes this is really useful. Sometimes it's not useful at all. Okay. All right, moving along. What if you want to go the other way? So notice all the examples I've shown you so far, the parameterization was given. Here's a parameterization. What is it? So let's entertain now the question of going the other direction. Suppose somebody comes to me with a curve. I know what the curve is. but I need to produce the parameterization. So this is called parametrizing, the act of creating a parameterization from other known information about a curve is called parametrizing the curve. So there again, various different tricks, various different tools, none of which always work. It's tools for your toolbox kind of a deal. So I'm going to start with my favorite. This is my desert island parameterization method. It's called the graph parameterization. I love it because it's so easy. It's so easy. Now it only works sometimes. Again, tools for your toolbox. This only works, I cannot emphasize this enough, if in fact you are talking about a graph. So a graph is a curve that satisfies an equation of this form. In other words, where I'm going to say y could be either variable. Let's just say y. Y is a function of x. More generally, one of the variables is a function of the other variable. Now, sometimes this works. Some curves are graphs. Some curves are not graphs. Right? Now, y'all will remember from high school math long ago, I don't know which course they cover this in these days, but there's this idea of the vertical line test. Y'all remember the vertical line? Do they still call it the vertical line test? Okay, yeah. Some curves fail the vertical line test. Those are not graphs. Okay, but if it is, then here's the simple method, and it's as easy as this, and I love how easy this is. If you have a graph, let t be the input variable, whichever variable is going into the function, as opposed to being the thing that comes out of the function. Whichever is the input variable, call that t, declare victory. Pretty much, it's that simple. It's awesome. Okay, let's see an example. Let's see here. Okay, so let's look at this equation right here, and we notice that is indeed a graph. It is indeed in that form. Y is a function of x. So now I'm going to follow the instruction. I'm going to let t be the input variable. In this case, the input variable is x. I'm going to let the formula for x be just t. I claim it's already over. We've already won. We just have to, kind of run it into the end zone. Here's the big idea. If x is t, plug that in. That kind of forces you to make y equal to t squared. Check it out. We have position as a function of time. Again, touchdown, we win. It's that easy. Everybody on board? Super cool. When it works. Okay, now here's another example. Let's look at this equation. Let me clean up my mess first. This is distracting. Let's look at this equation right here. Now, real quick, is this equation written in the required form? Is one of these variables written as a function of the other? And well, at the moment, no, it's not. And if I were to take a naive glance at this, I might come to the wrong conclusion because I look at that y right there and I see that y right there. Can I solve for y? No, that's you just can't. Right? This is what we call a transcendental equation. You cannot solve for y as a function of x algebraically. Okay, that's too bad. But remember, it doesn't have to be y that you solve for. It is perfectly fine to solve for x. And notice I certainly can. And so now I have it in the desired form. This is one of the variables as a function of the other. X is written now as a function of y. And so, cool, graph parameterization kicks in. Y is our input variable. We let that input variable be the parameter t, following the rule, right? The rule, back up to here. The rule is that t is the input variable. We're letting t equal to the input variable, and then again, my hands are kind of tied at this point. And if y is equal to t, well, then that kind of forces me into x being this function of t. And again, victory, position as a function of time, and that's a parameterization. Everybody with me? Okay. Right. Okay. Now again, tools for your toolbox. Again, this is my favorite parameterization method, but there are others. This is a kind of a neat one. There are a lot of details in this example. The broad stroke on this is to use vector algebra. I'll get to that in a moment. Let me first define what the scenario is here. I have a wheel that's rolling on the x-axis, like the x-axis is a road, and it's rolling to the right. And I don't know if y'all remember, I'm sure you've noticed this at some point, when it's kind of dusk or, early evening and the street lights are on and somebody's riding down the road on a bicycle and they have the reflectors on their bicycle, and you see that kind of jerky, kind of lumpy little pattern that the reflector makes, right? Well, that's a curve. Let's parameterize that curve. It's a weird curve. How are we going to do that? Right? By the way, your first instinct might be, because y'all have seen equations since long ago, and you've seen graphs since long ago, the idea that y is a function of x is an old concept. You might be tempted to try to write the equation or to view it as being a graph of some function, and that's going to crash and burn. It does not work well. I don't want to say it's impossible. It's really undesirable at best. It turns out it's actually not that hard to parameterize. And the big idea, well, there's three big ideas here. I'm gonna hit the big ideas. I'm gonna leave the details. This is a helpful exercise to go through and think through all the little micro details. It's just trig and geometry and a little algebra and just being careful, right? There's nothing fancy in that I'm going to skip here. But here are the three big ideas. First is the idea that the reflector, let me get my colors straightened out here. The reflector here, which after it rolls a bit is there. And so here's the wheel at time equals 0. Here's the wheel t seconds later. As it rolls like that, the reflector will be up to there. Yeah? First big idea, that is equal to, color choices. It's equal to this blue vector describing the location of the axle of the wheel plus this green vector describing the direction and magnitude of the spoke that reflector is attached to. So we have this complicated thing, right? The position of this orange reflector, which is making this wacky curve that's, doing all sorts of weird stuff like that, is the sum of two simpler vectors. And I say simpler vectors because if you look at the axle is moving pretty much in a straight line. That's actually not that much trouble to write a formula for the position of the axle. It's always at the same height. Right? It's moving at a constant speed, we're assuming, for the purposes of this problem. And then the green vector describing the direction and magnitude of the axle. Don't fall for the easy mistake. It's tempting to say, but that axle is doing some funny business like this. Now, the axle, the spoke is represented by a vector, because it's a direction and a magnitude, and vectors don't have location, right? Vectors, direction and a magnitude. And so as the wheel rolls, that green vector is just going around in a circle. Nice, friendly little circle, nothing to it. So weird curve is the sum of something easy to describe plus something else easy to describe. That's the first big point in this situation. Everybody see that first step? Okay, second big point. This is really important. You have to be very explicit and deliberate about what your parameter is going to be. There's a lot of different things that you could choose to call t, or whatever other parameter you want to use. There's a case to be made that any one is just as good as any other, but there are some that are going to be more convenient. When there are angles involved, and when the motion in question could be described by an angle, I think it's really valuable to let t be that angle, because it's a lot easier to write trig functions than it is to write inverse trig functions. Right? So for your consideration. So I am going to suggest that we let t be this angle right here as I have it labeled. So measured off of the straight down direction, measured clockwise, which is the way the wheel is rolling, clockwise from straight down, we're going to call that angle t, measured up to the spoke where the reflector is. And notice that we start with t equals 0, and as we roll to the right, t is increasing as time should. Right? You don't want to set it up where time's moving backwards. It's a little creepy. Right? So pretty reasonable way to set it up. So now again, there are different choices you could make. I think this is hard to argue with as being probably the easiest one. But the big point, make sure you're explicit. You need it in your diagram, clearly labeled. You got to make sure not only do you know what you mean by t, but you got to make sure that your reader knows what you mean by t. Otherwise, everything you write down is kind of meaningless. Okay. All right, and here's the last big point. This is a tricky physical observation. Let's go back to thinking about the axle. So the axle is this point right here. It has an x and a y coordinate. The y coordinate, of course, is easy. The y coordinate is just a. It's the radius. It's always the same. That part's freebie. But let's think about the x coordinate, which is this distance right there. And how can I relate that distance, the x coordinate of our axle, how can I relate that to t? And here's the big physical observation, super clever observation. Notice that x coordinate is a length of road. Specifically, that x coordinate represents the amount of road that has touched rubber. Right? As this wheel has rolled along, right? The wheel started with the rubber touching there, the rubber was touching there, and at this moment the wheel is touching there. So this is the amount of road that has touched rubber, and I argue that the amount of road that has touched rubber is equal to the amount of rubber that has touched road. You just got to think that through physically. This is not a mathematical argument. This is a physical appeal. This piece of rubber right here is what was touching the road initially. And then as it rolled, the part that was touching the road kind of moved like so until now, at this stage, it's that point on the wheel that's touching the road. So basically, all this is saying, all my physical appeal is saying, is that the wheel is not slipping. There's no skids. So road equals rubber. Everybody buy it? And of course, this dark blue distance here, this is an arc length. It's an arc length where I know the angle. High school geometry kicks in. It's all downhill from there. Okay, so now again, I am going to leave the rest of the details for y'all to think about. This is a really good exercise. There are little details to be careful about. You want to make sure to be appropriately careful. In situations that require care, you've got to be appropriately careful. Think about all this stuff. A tricky point you definitely want to keep an eye on is, why does this diagram tell me that? Spend some time thinking about that yourself. And as always, come to office hours if you have any questions. Of course. Help room, ask a friend, blah, 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 right? But seek help. I'm happy to talk with you. But you put those together and out comes the answer, which is that. So impossible to write it as a graph of a function, impossible to write it as a solution set to an equation, merely inconvenient to write it as a parameterization. Okay, moving along. Another example. Here's a common scenario. We have here a line. I would like to get some algebra on the board to describe this line. In particular, we're going to try to parameterize this line. Now, if you're going to ask me to parameterize a line, you got to be specific. You got to tell me exactly what line are we talking about here. So I'm going to presume, in this case, that we know a point on the line. Doesn't matter which, just any point on the line. And I'm going to presume that we know a vector parallel to the line. Now, again, geometric appeal. If you tell me, hey, I'm talking about the line that goes through this point and is parallel to that vector, that characterizes the line. Right? There's only one line that goes through that point and is parallel to that vector. Is that cool? All right, so how do we do it? How do we create the parameterization? Clever observation to be made. That point, right, keeping in mind we have that vector, that's all given. Now let's suppose I have some other point on the line. Geometric appeal. If I have another point on the line and I also had the original point on the line, if I look at the difference, right, that difference vector is parallel to the line, geometric appeal. And if it's parallel to the line, and of course V in the first place was parallel to the line, then this green vector is a scalar multiple of V. And so I can write it as TV, just a scalar multiple of V. All right? Okay. So, cool, we're done. Position, you can see right here in the picture, is x0 plus TV, that being, of course, just a scalar multiple of the given vector V. And so if you give me an x0, you give me a V, there you go. There's a parameterization of that line. Everybody happy? Okay. Here's another one. Again, we're just, I'm filling up your toolbox, the different methods that work in different circumstances. Let's parameterize now, if we can, this ellipse that has this equation, something like that. How would I create a parameterization of that ellipse? So, starting with a geometric appeal, I'm going to make two little geometric appeals. For one thing, I already know how to parameterize a circle. Right? That's, again, the first parameterization we saw. Second part of the geometric appeal, ellipses result from stretching circles. So, you look at this ellipse, you look at this circle, it would seem that I need to stretch in the x direction by a factor of 3. And I'm going to stretch in the x direction by a factor of 3 like so. I'm going to take my existing parameterization of the circle, cosine and sine, and I want to stretch in the x direction by a factor of 3. So I'm literally going to make those x coordinates 3 times as big by literally multiplying that formula by 3. Yeah? Likewise, apparently I need to stretch in the y direction by a factor of 2. Again, easily accomplished by multiplying that y coordinate formula by 2. and out comes a parameterization of our ellipse. Everybody on board? Now, if you are uncertain whether this worked, I mean, visually it's pretty satisfying to say that, okay, the blue is just a stretched out version of the purple. But is it exactly that, or is it just kind of like that? How do I know that this actually works? And this is actually an easy confirmation, because I can take this formula right here and I can straight up plug it into that equation and it just full on works. So we declare victory. Everybody good? Okay, so now here's a subtle point. A lot of people, look, a lot of high schools they make bad habits in students, and students eventually notice that they can kind of notice certain patterns and can avoid sort of precise, rigorous thinking by just sort of, you take this here and you kind of put it in there, just kind of noticing the patterns. One of the problems that I encounter a lot is that a lot of students will look at a parameterization and just conflate that with an equation, because they're algebra that we use to describe a curve. Right? An equation is algebra that we use to describe a curve. A parameterization is algebra that we use to describe a curve. So whatever, right? It's tempting to be a little sloppy about that. So I think it's really important that we not be sloppy. I think it's really important that we see exactly what is the relationship between a sort of algebra that we use to describe a curve and the points on the curve themselves. So keeping in mind, parameterization is position as a function of time. Right? So said differently, points on the curve are outputs from a parameterization. On the other hand, that is not how equations work. Equations take a point on the curve as inputs into the equation. You take a point that you think is on the curve, or that you hope is on the curve, or that you're wondering if it's on the curve, and you plug it into the equation, and you see if it works, and it either does or it doesn't. And if the equation works, then yes, that point's on the curve. If the equation fails, then no, that point is not on the curve. Right? So you see the difference here. So there is a big difference between how points relate to parameterizations versus how points on the curve relate to equations. The former are outputs, the latter are inputs. Okay, so let's just keep that in mind. And a little bit of language, I like to refer to a parameterization as a point generator, because it's literally producing points. And I like to think of equations as point testers, because it's something I can put my points into and out comes either a yes or a no. That's a test. Okay, so I like this language, and you're going to hear me use that language here and there throughout the course, so heads up. Okay, so that in mind, here's a lovely little question, and I think there's at least one homework exercise that is very, very, very similar to this. Here's a parametric curve, and I want to know what points on that parametric curve are also on that plane. So where does this curve intersect that plane? So we've got a point generator, we've got a point tester. So here's the big picture. We're going to generate points and then test them. Okay? So here you go. Here's generating points on the curve, right? These are all points on the curve. The outputs of a parameterization, point on the curve. How do you test points? You test points by taking that x, y, and z and plugging them into the left side of the equation and seeing if you get the same as the right side of the equation. So notice that's all I've done here. I've taken a generated point and I am testing it. Right? And when I say testing, keep in mind that I am literally taking this formula for x and plugging it in where the x goes. And I'm taking this formula, colors, come here, colors. This formula for y, and I'm plugging that in where the y goes. And, colors. This formula for z, plugging that in where z goes. And now it's just algebra. Now it's just, it's all downhill. From here, you take this equation, manipulate it around, it becomes this. It's not hard to solve. You get those values of t. And don't celebrate too early. We have successfully found now the correct values of t. That's not actually what the question asked. The question asked for the points. Keep in mind the points are what come out of the parameterization. So you've got to take these values of t, plug them into the parameterization, like so, see what you get. Those are the points. Is everybody happy? Feel free if you got a question. All right. So I think it's a cool. It's a cool exercise, and also it's a lovely illustration of why it's important to understand these 2 points of view. Maybe I'll say this distinction between how parameterizations versus equations describe curves. Okay. This last little thing, I'm going to be real quick about this. How do we create a point tester? What you might want to call an equation for a line in R3. Can we write down an equation for a line in R3? Well, an equation would typically give us a surface, as I mentioned before. So it wouldn't typically give us something like a line. Fine. So I don't technically need an equation, but if I just want to have a point tester, I want to have, look, I've got a point, I need to know if it's on this curve. I'm open-minded as to how I make that determination, but I need a convenient way to take a point, and yes or no, I want to know if it's on my curve. Okay. So here's the clever idea. We start off with a obvious smart alecky observation, and that is a test for whether a point is on the line. One could argue is, okay, well, yeah, does there exist some value of t that I can plug into there that makes my parameterization actually produce that point? So I call this a smart alecky answer because it's not particularly helpful, right? Yeah, I mean, of course, if you can produce it with the parameterization, then it's on the line. But this is not helpful to me because how in the world would I know if there is or is not some appropriate value of t? What am I going to test all the values of t? There's too many. I can't test all the values of t. So not particularly helpful as written. Yeah, please.
Is that reversed notation?
Yes, I always forget the terminology and notation. So this is a mathematical shorthand for there exists or there is. And this other symbol here, kind of a weird looking symbol there, that means such that or so that. Yeah. Thank you for, yeah. All right. Yeah, okay, so again, there's a clever move. The clever move is as follows. If this vector equation is going to work, then likewise, I would need all three coordinate equations to work. The three coordinate equations, I can solve for t. let's see here. Yeah, take that t right there, and you solve for it in all three of those equations. So, in the first equation, that's what you get when you solve for t. In the second equation, you get that, and in the third equation, you get that. So now all I've done, I haven't really done anything. All I've done is solve for that t, and I get these three things. Now let's rewind, take a pause real quick. What was the point of all this in the first place? Well, I need to know if there is a value of t that makes this work. Is there a value of t that makes this work? Okay, well, let me say that differently then. Is there a value of t that makes these three equations work? Rhetorical question. Okay, well, let's think about that for a moment. Is there a single value of t that makes all three of these equations work? Well, it kind of depends on what these values are, doesn't it? If these three values are, let's just say, if those three values are 2, 2, and 6, is there a value of t that's equal to all three of these numbers? No, of course not. There can't be a value of t that's equal to both 2 and 6. That's silly business. It's hopefully clear that if I ask, is there a value of t that's equal to 2, 2, and 2? Yeah, 2. Right? Silly, but it becomes very immediate then that the answer to this question is going to be that I need these three things here to equal to each other. And this here is called the symmetric equations, plural. Importantly, plural. Not singular. This is not an equation. This is two equations. Right? Arguably three, because there are three things that have to be equal. But anyway, two equations, and this is the test. If all three of these things are equal to each other, yes, that's a point on your line. If these three things are not all equal, if any one of them is different from any other one, then that point is not on the line. So, yeah.
How would you test those points in a plane or in a subspace? Would you then just go through and test each component?
It's even easier. So for a plane in R3, it's going to turn out that we actually do have a single equation.
Okay.
Yeah, we'll get to that later on. That's a couple sections forward. Yeah. Okay. All right. Cool move. Whoa. Cool move. Okay, moving along to 1.3, dot products. Y'all have seen dot products. I know you've seen dot products. So again, tough choices. We're going to move real quick through this. The old formula. Y'all remember all the properties. They're in the book. Don't forget this is a model for inner products. It's where inner products come from, right? I do want to hit one thing here. This is a kind of a pet peeve, but I think this is an important distinction that is underappreciated. Our book, and frankly, many books and many people are a little sloppy on what I consider to be a non-trivial point, and that is that they use these words interchangeably. I think that's unfortunate. When I was coming up, right, I wasn't brought up right either. I was always told when I was a kid that orthogonal is just a fancy word for perpendicular, and it's really importantly more than that. So here's the distinction as I see it. The word perpendicular, to me, is a geometric idea. Perpendicular is a reference to directions and the angle between those two directions. And now, quick observation, direction is a geometric concept. Angle, right? Angle is an intrinsically geometric concept. So perpendicular is a geometric idea. And now, quick observation, you can't talk about the angle between two directions if there is no direction. Right? And of course, the zero vector doesn't point in any direction. So the idea, this word perpendicular, being intrinsically geometric, is for non-zero vectors only. Okay. Now, let's talk about the word orthogonal. Orthogonal, to me, is an algebraic thing. It's about dot product being 0, or more generally, if you're doing linear algebra, if you're in inner product space, then it's where the inner product is equal to 0. That's an algebraic thing. And there's a strong relationship. Sure. But let's not get into the conflation yet. Let's make the distinctions first and then connect the ideas. This algebraic idea does not directly and immediately have any geometric manifestation. Right? This is a dot product is defined with algebra. This is an equation. That's an object of algebra. This is all algebraic talk. So sure, there is a relationship, and whenever you have two non-zero vectors, then perpendicular and orthogonal are simultaneous. Yeah, sure, right, fine. But one of these words makes sense if you're talking about the zero vector. The other one doesn't make any sense at all. One of these allows for the zero vector. The other one does not allow for the zero vector. So you got to be careful. And again, I'm going to confess in advance. I mean, I wasn't brought up right on this, and I've done my best over the years to try to train this out of myself. But I will sometimes say perpendicular when I meant orthogonal, and I will sometimes say orthogonal when I meant perpendicular, and I'm sorry in advance, and I'm doing my best. Please call me out on it. Absolutely, right? And I will call out myself on it as well when I catch myself. But I think it's valuable to make this this distinction. After all, we don't need two words to represent one idea. We have two words. We have two important ideas. Let's pair them up and maintain that distinction. And I'm out of time. Okay, so we'll draw a line right here, picking up here on Friday. Y'all have a good rest of your day. See you later.